My name is Jim Davies. Terry always gives us a very interesting presentation and covers a lot of ground. And the document he's been talking about is this one, Subdivision Guidelines, which is the IPWEA document. And of course, today we are here as IPWEA. We're here as an engineering fraternity rather than environmental. And as Terry said, a lot of our discussions are going to be quite technical. Now, on the programme, it does say that this talk is prepared by myself and John Argue from South Australia. In fact, I didn't get a chance to involve John in it, so I've written it myself. I am hoping to enlarge on this for a SIA conference later this year in Melbourne with John. I haven't prepared a paper on it, so there is only the slides, which I'm happy to make available to anybody who wants them. So I think Terry did stress the importance of stormwater quantity rather than quality, and that's really what my talk is about this morning. It's not about nutrients or receiving waterways. It's very much about stormwater quantity, and in particular, I've called it "How much runoff?" ? So I'm really taking us back to basics for half an hour to consider how much water do we really have to deal with in our stormwater drainage systems. And I suppose the emphasis of my work as a consultant is usually on new subdivisions. And as Terry said, we should all be doing what we can to make subdivisions cheaper. And as many of you will know, the drainage aspect is very expensive, particularly the amount of fill that's being brought in on new subdivisions. But in terms of this talk now, I suppose what I'm asking for is more realism, more thought be given to just how much water do we have to deal with, and whether perhaps we are over-designing our stormwater systems. When you think about the storms we've had, I recall February 92, which was a weekend storm. It was a 100-year. And there was very little flooding in Perth as a result of that. And that first made me start thinking that perhaps we are over-designing our drainage systems. So I'm digressing a bit at the moment. There was a comment at the back to Terry. What about maintenance of stormwater systems? I suppose it was brought home to us all on March 22nd, 2010, when we all saw the inlets to the stormwater system being completely blocked by what happened during the event itself. So it really was a lesson that no matter how well you maintain and clean your stormwater system, in a big event like that, it is probably going to get blocked. And the water is not going to get into the pipes probably at all, and it's all going to go overland. Not that anybody's documented that, but that was my experience of it in Subiaco, Netherlands area on that day, that no matter how much we maintained and cleaned gullies and pits, in the storm itself, all the vegetation came off the trees and blocked all the inlets. So that is a real problem when you get a major storm. Anyway, I'd better try and focus in on the talk, and I'm getting there gradually. I did look at the programme coming in. We've been encouraged to talk about a brighter future, creating a brighter future. Well, actually, for many of us in the room, I think we've had quite a bright past, actually. Living in Perth for the last 30 years as I have, it's been quite a bright past. And to think about creating a brighter future, how am I going to wind that into my talk? Well, I suppose what I'm thinking is if we can make it a more affordable future for the younger people looking to buy houses, if we can make stormwater more interesting, and if we can make the way we design things more meaningful, that's probably all part of a brighter future. Okay. So over the years, I have liked to give talks at the IPWEA annual conferences. I find it's a great venue to put some ideas across and get some feedback. So that's what I'm hoping to do today. Okay, now I'm going to make a start. So what I've called this is runoff coefficients. So we all know what I'm going to talk about is how much rainfall becomes runoff. Essentially, that's what I'm talking about, and I think you'll all have that idea. And already Terry has said, you know, when you urbanise an area, the road reserve is probably going to have 95% runoff coefficient. So Terry's already loosely talked about what I'm going to go into quite a bit of detail about. What does Terry actually mean when he says 95% runoff coefficient? I suggest to you what he means is, if you're using the rational formula, you'd have a coefficient of runoff of 95%. I suggest that to you. I'm happy to take discussion during this talk, by the way. Okay, so I'm starting just with the water cycle. I think we have got a pointer here. Yes, okay. So the normal sort of water cycle of rainfall coming in and evaporation. And I'm really focusing on this one here, which is stream flow, or what we would call in the urban area stormwater. So this is very much a rural landscape. I'm talking really about urban areas this morning, but it is that component of the water cycle which I'm focusing on, the surface runoff component. Okay, so when we talk about runoff, we mean that part of the rainfall which flows over the surface. And the runoff can only be generated in two ways. It can either occur when the rainfall rate exceeds the soil infiltration rate, and that's called infiltration excess runoff, or when rainfall lands on saturated surface. So for the first one there, most of Perth is sand, and you just about never see runoff from the sand. And I am thinking again about March 2010. I think for the first time I saw it. Coming out of King's Park, there was water actually flowing out of King's Park and over Thomas Street there, opposite the hospital. I've never seen it before. I think for once the rainfall rate was high enough to actually create some runoff from sand. Of course, if you've got a clay soil, you will get runoff because the infiltration rate is less, so you will get some runoff.
Runoff as well as on impervious surfaces?
Yes. Impervious surfaces like roads, yes, will definitely create that runoff in that first way. As part of that. Now this second one, when rainfall lands on saturated surface. So in the older parts of Perth, we never had this. The land was higher than the water table. But in a lot of the new areas, in Armadale and SJ and Murray, the water table's almost at the surface. So you get runoff just because the water can't get into the ground. So that's the two mechanisms by which we can have runoff generated. So this notion of a runoff coefficient, I think we all probably use it in our working days, every day probably. But what do we actually mean? It's a term widely used in hydrology and drainage, and it's got different meanings in different contexts. And it's a ratio, and it doesn't have any dimensions or units. So the first meaning, which I've got there, is the fraction of rainfall which results in surface runoff. So by that we would mean, if you have 10 millimetres of rain in a storm, and you get 5 millimetres of that becoming runoff, that would be a 50% runoff coefficient. And we would call that a volumetric runoff coefficient. It's the proportion of rainfall which becomes runoff. And that is quite different from what I believe Terry was talking about earlier when he said 95% runoff from a road reserve. Knowing Terry, I believe he was thinking of Q equals CIA, the rational method, and in that, the value of C is the ratio of rainfall intensity to peak runoff per unit area. So there are these two different definitions of runoff coefficient. The one is the fraction of rainfall which becomes runoff. As I said, like 5 millimetres of runoff from 10 millimetres of rain will be 50%. And the other one is this ratio of the rainfall intensity to the peak runoff rate. And I think, as most of us probably use these terms interchangeably, And I think I might be the only person in the room who's tried to work out, well, are they the same thing? Because I have posed this question to a lot of eminent people across Australia, and nobody has given me an answer to this. So I've tried to work it out. Does anybody think it's worth trying to work it out? Or does everybody think, why is this guy up the front today? Does anybody see it as a problem? Okay. The way I see this as a problem is that if you could do this, like Terry does, and you use a value of 95% in that one, and then you've got a younger guy in the office who wants to use XP Storm or some other hydrograph method, he will say to Terry, well, what value of runoff should I use? What's the volumetric runoff coefficient that the model's asking for? And Terry will probably say, well, 95%, I've just told you. But they are not the same thing. They are not the same amount. Numerically, it's not the same value, and I will come to that shortly.
What I'd like to know, though, is if you use that 95%, that means you're designing your whole capacity, or you are doing it excessive design if you use 95%? Is that what it means in XP Storm?
Over design. Well, I'm not really going to come to that because my overall view is that we need to do some monitoring, because as a consultant I'm doing drainage designs and I'm giving them to local authority people like yourselves for approval, and the response I'm getting is, why have you used 30% runoff? Why don't you use 40% or 60% or 70%? So between us, I think we need to collect some data. That's one of my main messages today. I don't think there's any catchments that in Perth that are being monitored to help answer this question. And I do think overall we are over-designing.
But putting it in a simple context, if you got a surface which is 100% infiltrable, right, you're going to have a runoff of 95%. That's a fact. It's not proportion of 10 millimeter rain is going to convert into the runoff of 5 millimeter. It's not, because you're clearly, so how
Okay.
the image is going, you're assuming it's going to be infiltrate into the ground where it isn't.
Okay, I don't think any of us are disagreeing. If you've got a bitumen surface, a road connected to an outlet, it will have 90-95% runoff. The discussion is really about what about the rest of the catchment? What about the lots? What about the housing lots? What about the public open space? How much runoff will it generate?
The housing lot mostly has got a tie roof, which is again infiltrable. Once the verge is saturated on first rain event, it's almost there is no way, because the bitumen surface with the limestone underneath, no way for water to go.
Okay, let me carry on. So this is what I could find in the literature. This is out of a new textbook by Ladson, 2008. He's actually in Brisbane. It's the first book on Australian hydrology. I like it very much. He talks a lot about Perth. So he suggests we have an initial loss, and then we have a proportion of loss. So he has this table of data for different catchments around Australia. There's nothing there for Perth. And that's because none of us in the room has actually done any calculations on this. We're all running models and making estimates, but we don't actually have any data to show for Perth. So this is fraction impervious here. So the highest number he's got here is a catchment in Canberra. He's got about 35% impervious fraction from a catchment. Okay, so yes, individual roads would be 80-90%, but when you look at the catchment as a whole, his view is it's a maximum of about 35%. I've gone back to this. So there I've been talking about that. Now this definition can apply to a storm or a month or a year. This notion of the volumetric runoff coefficient. So over a year, you could say we've got 800 millimetres of rainfall, we perhaps only get 100 millimetres of runoff. So that runoff coefficient might be a lot less on an annual basis than on a storm basis. Now this second definition, the rational method. this is the rational method. I trust most of us are a bit familiar with this. It gives us the flow rate, there's a factor for the units, there's the rational method runoff coefficient, there's the average rainfall intensity over the time of concentration, and there's the catchment area. Now this is taken out of John Argue's book in 1986, which some of you might be familiar with, Stormwater Drainage Design. So he shows here, this is an impervious catchment now we're looking at. Not a mixture, this is an impervious catchment, and 0.1 hectare, and he tells us that the time of concentration is 20 minutes. So this is an IFD curve of rainfall intensities. So I've just marked there, time of concentration is 20 minutes, that's the intensity. If this is all for 10 years. If you go to a longer duration, like 60 minutes, you'll have a lower intensity for that same ARI.
What does that mean? Time of concentration?
Okay, time of concentration is really the travel time from the furthest point in the catchment to the outlet. So the notion of this rational method is that the critical storm is the one which just ends when the water from there gets to there. That's called the time of concentration. So if it rains for longer than that travel time, then the intensity will be less for a given average recurrence interval.
And it's also quite tricky to actually calculate that accurately.
Yes, that's quite tricky to estimate it, but the concept is, and similarly, if it rains for less than the time of concentration, like if it rains for just 10 minutes, then when the rain stops, the water from there won't have got there. So when you put this and this together, this is how John Argue plotted it. That is the 20-minute storm there, reaching that peak flow. He's labelled it number 3. If you get a longer storm, like an hour, it still peaks after 20 minutes, but it's not such a high peak. So this is the rational method. You work out your time of concentration and you work out your peak flow for that. Now, that is really what the rational method gives you, is that flow rate. It doesn't really give you the shape of the hydrograph. It doesn't really tell you that that's a straight line, and it doesn't tell you that this is a straight line either. But that is how John Argue has drawn it, like an isosceles triangle, the time to peak equal the time of fall. And once you draw that, then you can work out the volume of runoff. Right? Because the rational method really only gives you the peak flow in meters cubed per second. But if you assume a shape for this hydrograph, you can then work out your volume of runoff. So I've had a look in Australian rainfall and runoff, which is a document that the subdivision guideline refers to. And this does stress that the methods we use should be based on observed data. Methods of flood estimation should be based on observed data from either the catchment itself or representative catchments. Now, most of us are probably not doing that at the moment. We're sort of guesstimating what we think the runoff should be. So collectively, we're probably out of line. And later in the same document, it does say, again, runoff coefficients must be based on observed data, not arbitrary values based on experience or judgment. So the Engineers Australia document doesn't actually like experience and judgment. It likes observed data. And it specifically refers to this figure, which some of you might be familiar with. This is actually out of the 1987 publication rather than the new books, but it's the same figure. So Perth is roughly on this line. This is the 10-year 1-hour intensity of 25 millimetres per hour. So if we have a fraction impervious on the catchment of, say, 0.2, 20% of the catchment is impervious, we will get a runoff coefficient in here of about 20% for the 10-year. So that is what's recommended in Australian rainfall and runoff. And this is for the rational method, remember. This isn't for a volumetric method, which is what most people are using in these models like XP. And those are some factors to convert that into 100-year. So you work out your 10-year and multiply it by 1.2. So this says you work out your 10-year runoff coefficient, you multiply that by 1.2 to get your once in a 100-year runoff coefficient. Now what I want to really talk about today is what I've been doing lately, which is trying to understand this relationship between these two definitions of runoff coefficient. So I'm just going to spend a few minutes on this. So I've got here an example for a fully impervious catchment. So this is, if you like, something that's fully bitumenized, like the runoff catchment on Rottnest Island used to be to collect water, bitumen sloping down to a point. And I've done the calculation based on the numbers in John Argue's book, just for an example. And as I say, if we make some assumption about the time base of this runoff hydrograph, I've drawn three options here with longer and longer recessions or tails. So if we assume that the flow increases to a peak and then comes back down again, so that time base is twice the time of concentration, then we get the result that the volumetric runoff coefficient equals the rational method. So that's probably what you all want to hear. If you've got a catchment that's fully impervious, these two coefficients have to be the same. That's the way it works out. Now you see what I've hand-drawn this. That just goes up to there. Now on the next one, I've halved that peak. I'm looking now at a runoff coefficient of half of that, a value of 0.5. And this is now where we've got more pervious. We've now got some ground that's not bitumen. It's soil and it's grass. And it's going to take some water in and it might release a little bit later. And under this condition, we're likely to have a longer recession. The flow's likely to last a lot longer. And so depending how long it lasts affects this volumetric runoff coefficient. So if the time base is the same as I showed before, straight up and straight down, you will get the same volumetric one as the rational. But if it's got a longer time base, as I suggest it will, then this volumetric runoff coefficient has to be a lot higher than the rational method coefficient to get the same peak. So I'm all about matching peak flows here by these two methods. And I haven't seen anybody do this before, so it's something that I'm putting in front of you to consider and think about. So I haven't run any models to do this. I've just assumed some triangular hydrographs. So I suggest to you that in a typical urban catchment, we might have a 0.5 rational method runoff coefficient. We've got some roads, we've got some runoff from the lots, maybe some of them are connected. You know, the back gardens probably don't drain, the public open space won't drain to the drainage system. So if we use that in a calculation, and if we want to get the same answer in a model like XP Storm, which uses a hydrograph, then we have to use something higher. We might have to use a value of 1, assuming all the rainfall becomes runoff, in order to match what we get with the rational method. So these are my conclusions. The IPWEA subdivision guidelines are silent on this notion. As Terry mentioned, March last year we had the workshop in here. That was one of the subjects that was briefly touched on. I think I might have raised it from the audience, and Terry said that might be a good thing for the foundation to fund a project on that. Well, nothing's happened on that, but I do think IPWEA should probably take a lead here and develop some coefficients of runoff that would apply to all of us. They may be different for different soil types, different local authorities, but I do think IPWEA probably could take a leading role in that. So then I quote this new textbook I've just referred to. There's the AR&R recommendation on how you do it for the rational method. I think we need more consistency because, you know, if I do a project, other consultants are doing projects, we're all coming up with different numbers. I'm sure at the local authorities you don't really know which one to accept. And then to match flood peaks, this volumetric runoff coefficient must be greater than the rational method. So I think we need a better understanding of these different definitions of runoff coefficient. Thank you.